This is a video lecture for Math 140 for Thursday, April 23rd. This is part one of the video lecture. And the topic today is the law of cosines. Now in the last two classes we've been talking about the law of sines and applying the law of sines to three different types of non-right triangles. And those triangles are the AAS triangle, the ASA triangle, and finally the SSA triangle. And this last one was an ambiguous case, so we had to be particularly careful in how we applied the law of sines to this last triangle. But we were able to apply the law of sines to solve all of these triangles. And it might make you wonder, is law of sines all we need to solve any triangle? Well, the answer to that is no. And what I want to do is to motivate that, I want to consider two types of triangle. One is an SAS triangle. So this is a triangle where you know two sides and one angle that's sandwiched between those two sides. Okay. Now the problem here with using the law of sines, which I've written right here to remind ourselves, is if we call this angle A and side A, we could write sine of angle A, sine of 20 over side A. But then we need to relate that to another angle side pair. But we don't know any more angles, right? We don't know this side length A, and we don't know another angle we could plug in for either sine of B or sine of C. So automatically we're going to have two variables, two unknowns in our equation here in any version of the law of sines we use. And we will not be able to use the law of sines, at least initially, to solve this triangle. Okay. Also, we could have an SSS triangle in which you know all the sides and none of the angles. Now this obviously you can't apply the law of sines to, because in any version of the law of sines here, we need to know at least one angle. You know, so if I look at A and B here, right, I don't know either angle A or angle B. So automatically I have two unknowns, and I can't use the law of sines to solve this triangle either. So we obviously need another tool, another law, to treat these two particular triangles. And that law is the law of cosines. And what we're going to do now is we're going to do a derivation of the law of cosines. Now, the derivation of the law of cosines is a little more complicated than the derivation of the law of sines. And you guys won't be responsible for this on the test, except possibly as an extra credit problem. But it is a really nice, beautiful, fun derivation. So I want to do that derivation. And then in the second part of this video lecture, I will apply the law of cosines to these two types of triangles to solve them. So let me erase this, and we're going to do a derivation of the law of cosines. Okay, I need to be careful here drawing this triangle, so just give me a moment to draw this accurately. I'm going to have a coordinate axis system here, x and y. We're going to have some triangle here that goes up like this, that comes down like that. Okay, and this will be angle A here. I'm going to call this angle theta as well, same angle. Okay. And that means this is side length A. And then I'm going to call this angle B, and this is side length B, and this is angle C, and side length C. Okay, so this is the triangle of interest, and I'm going to derive the law of cosines on this triangle. Okay. The first step here is let me relabel this. This is A right here. I'm going to, as a first step here, I'm going to drop down a perpendicular, okay? And I'm going to call this distance x. So the distance along the x-axis to the point where this perpendicular hits the x-axis is called x. I'm going to call this distance right here y. This A right here, this triangle is located at the origin 0, 0. Okay. And the first thing I'm going to make an observation here. So now I have my original triangle. Now I've dropped down a perpendicular. I've created two more triangles. I now have two right triangles in addition to my original triangle. I have this right triangle and I have this right triangle. Okay. So what I'm going to do here is I'm going to take the sine of angle theta. Okay. I'm going to take the sine of angle theta on this right triangle here. Okay. If I do that, remembering that sine of theta is the opposite over the hypotenuse, sine of theta here equals y over b. This is the opposite, this is the hypotenuse of that right triangle. And now if I solve for y, I get y equals b sine of theta. Similarly, I can take the cosine of theta, okay, and the cosine of theta is equal to the adjacent over the hypotenuse. The adjacent is x for that right triangle. So this is x over b. If I solve this for x, I get x equals b cosine of theta. Okay, so that's something to observe by definition of the sine and cosine. Also, I want to observe, let me just move this capital B over a little bit. This distance right here, I want to observe that this distance right here is x minus c. And so this is, I'm just going to write that, x minus c. And now what I'm going to do is I'm going to apply the Pythagorean theorem oh, I forgot to label this point right here. This point is point D. I'm going to apply the Pythagorean theorem to triangle BCD. So I'm going to apply the Pythagorean theorem to this right triangle right here. Okay, and if I do that, remembering the Pythagorean theorem says the square of the hypotenuse is equal to the sum of the squares of the other two sides. This means that a squared, because a is the hypotenuse of this right triangle, is equal to this side squared, which is x minus c squared, plus this side squared, plus y squared. So that's what I get. And now what I'm going to do is I'm going to substitute in here. I'm going to take what I learned about x and y and plug this into this equation. And so I get a squared. And now for x, I'm going to plug in b cosine theta, okay, minus c squared, plus, and for y squared, I'm going to plug in b sine theta, and then I square it. And then what I'm going to do is I'm going to square these out, okay? And if I do that, if I FOIL this out, I get b squared cosine squared of theta plus c squared plus my middle term. I'll let you guys verify the algebra of this. Minus 2bc cosine theta. And then this term squared is b squared sine squared of theta. Okay? And now what I'm going to do is I'm going to rearrange things a bit with this equation. If I do that, I get a squared equals b squared. Let me see here. 2bc. A squared equals b squared cosine squared of theta plus b squared sine squared of theta. I'm just moving this term over. Plus c squared minus 2bc cosine of theta. Okay. And then what I'm going to do is factor out a b squared here. And so this turns into b squared times sine squared of theta plus cosine squared of theta plus c squared minus 2bc cosine of theta. Now here, let's look at this. This is actually, we know what this is. This is the Pythagorean identity for sine squared plus cosine squared of theta. If you guys remember, this is just 1, right? This equals 1. And so that means I get this equation. A squared equals b squared plus c squared minus 2bc cosine of theta. And actually, here we know that cosine of theta is actually angle A. It's angle A, so I can just put in angle A for this. Okay, because theta is the same thing as angle A. So I get angle A here. And I'm going to box this. What I've just derived is the law of cosines. Okay, that's beautiful. That's a nice little derivation of the law of cosines. Now, let me just write this before we go on here. There's two other versions of this that are actually the exact same law. You can also write b squared equals a squared plus c squared minus 2ac cosine of angle B, and c squared equals a squared plus b squared minus 2ab cosine of angle C. These are also the law of cosines, and they're all basically the same law. So, I wouldn't memorize all three of these laws, just memorize one of the laws. They're all the same law. But the only difference is this law is applied to solve for side A, whereas this law is applied to solve for side B. This law is applied to solve for side C. And hopefully you guys see the pattern here. Like, if you're doing B, you just replace, in that case, you switch A and B to get this law. Here you switch A and C from this one. And so these are quite easy to get. And basically we can use these laws to solve any sort of, if you recall, an SSS or an SAS triangle. And what this is really saying is, in words, is saying the square of one of the sides of a triangle is equal to the square of another side plus the square of the third side minus 2 times the second side times the third side times the cosine of the angle opposite to the first side. That's kind of a mouthful, but that's what it says in words. One final thing I want to do is I want to show you guys kind of a clever little application of the law of cosines before we do some example problems. And that is, what if we apply the law of cosines to a right triangle? So what if I have a triangle that's a right triangle, okay? And this is angle A. Oh, excuse me, this is, side A, angle A. This is side B, this is angle B. And this is side C and angle C. What if I apply the law of cosines to this right triangle? Now you might think, well, why would I even need to use the law of cosines in a right triangle? You don't, but I just want to show you something kind of cool. If we apply the law of cosines, this says a squared equals b squared plus c squared minus 2bc cosine of angle A. But in this case, A is the right angle of 90 degrees. And that means cosine of angle A, cosine of 90 is 0. So this goes away, and we're simply left with b squared plus c squared. Well, what is this? What is a squared equals b squared plus c squared? This is simply the Pythagorean theorem. Okay, so what's cool is if you apply the law of cosines to a right triangle, it reduces to simply the Pythagorean theorem. Okay, in part 2 of our video lecture, we're going to do some example problems.